right, welcome everybody to another in our continuing series of lectures about physics and things that we're doing here in the department. The theme kind of for this semester has been things going on into the future, and so I'm going to talk a little bit about the future of X-ray astronomy and X-ray astrophysics, and I've dubbed that X-ray astronomy in living color. So it's going to be about spectroscopy in X-ray astrophysics, and I've shown a picture here on the slides. In the upper left-hand corner is a currently flying satellite, the Chandra-High X-ray Observatory. It's a satellite I worked for about 15 years of my career. It's been flying for a little over 20. It is still flying now. And in the lower right-hand corner is a mission that I am currently working on that is going to be proposed to NASA to be launched in the next decade or so, and the proposal goes into October. Let me say, and I'm going to ask everybody online if we can mute everybody. If you're listening online, please mute your speaker. Thanks. So, X-ray astronomy. Overall, let us talk about what are X-rays and why X-rays. So, as you know, light has two major properties to it. It has a wavelength and it has a frequency to it. And the wavelength times frequency is going to give you the speed of light, 300,000 kilometers per second. And the visible light that we're familiar with has a wavelength on the order of 6,000 angstroms, an angstrom being 1/10,000th of a meter. And X-rays, on the other hand, is a much more energetic form of light. Rather than having a wavelength of 6,000 angstroms, it has a wavelength of about 1 angstrom. And so to give you kind of typical sizes, long wavelength is low energy. Short wavelength is high energy. Long wavelength is also lower frequency. Short wavelength is higher frequency. So here's some characteristic scales. So radio waves is a form of light. They can be the size scale of buildings, of people, which is why when you see radio dishes looking at the sky, radio dishes can look like a chain link fence mesh, because as far as the radio wavelength is concerned, those holes that you see in the radio dish is shorter than the wavelength, so it looks like a flat, smooth surface as far as the radio is concerned. As we start going towards the optical, we're starting going to smaller and smaller time scales, length scales, and optical light is something on the order of typical microscopic organisms. As we go to ultraviolet, we're getting to the size of molecules. But as we get to the X-rays, we're getting into the range where we're talking about the spacing between the atoms. And that's going to be important for the kind of detectors that we actually use to reflect the light and to detect the light. So we actually have to make our mirrors a little bit differently than we do in the optical. So you're going to hear me in this talk use a lot of things kind of interchangeably, and I apologize that ahead of time. So for X-rays, the typical wavelength I'm going to be talking about is going to be about 12 angstroms. 1 angstrom to 12 angstrom is going to be the regime I'm going to be thinking about. So again, an angstrom is 1/10,000th of the light. Let's see if I can get my cursor back here and try to mute. There we go. Yes, mute all. Again, if we can ask people online to mute your thing. Thanks. So 1 angstrom to 12 angstroms, and equivalently in energy that I might be using to describe this is the kiloelectron volt. That's often, instead of using wavelength or frequency in X-ray astrophysics, we talk about the energy of the photon. So a kiloelectron volt is a very typical energy for an X-ray. Or equivalently, we also talk about temperatures. So the sun emits an optical light because it's about 6,000 degrees. If instead you were on the order of 10 million degrees, you would be emitting an X-ray light. So kind of keep that in your mind, that 1 kilo electron volt is about 10 angstroms, is about 10 million degrees. And that's kind of the numbers that we're talking about. So that means we can look at very energetic phenomena in the universe. So things that are highly energetic happening in a very small localized area leads to very high temperatures. Now, the goal for any astronomy is actually, it's rather straightforward what we do in astronomy. We basically count photons, and we bin up photons. All of observational astronomy really is an exercise in counting photons and binning up photons. And we describe this in terms of what's called the intensity. And we try to keep the math pretty simple throughout this talk. So don't get too worried about seeing the intensity list there. All the intensity is, think of it as a beam of light being directed towards us and coming towards us. And what we want to do is to characterize this intensity. This intensity is coming from some astrophysical source towards us. It is passing through material on the way to us. It is passing through gas in the intergalactic medium. It's passing through gas in the interstellar medium. It might be subtracted by this gas. There might be other sources in front that are adding to this. So our job is to measure this intensity and to characterize it and try to understand the sources that lead to subtraction from it or addition to it. And that comes to our detector. We want to measure that at our detector. And so what intensity is the number of photons passing through an area per unit angle on the sky, per unit time, and per unit energy. So it's kind of like a density of photons. So number of photons passing through an area per angle on the sky, per time, per energy. And all we're doing is counting those photons. Now we know for our satellite what the area of our satellite is. So that's taken care of in counting the number of photons. And then what we do is we count the photons and we bin them up. So if we bin up on angle on the sky or equivalently position on our detector, we're just making an image. So this is an X-ray image of the Crab Nebula pulsar. This is a neutron star. It's a few thousand light years away. This was seen by the Chinese about 1,500 years ago. And just by counting up the photons we see in the X-ray and binning that up, we get a lovely image of this in the X-rays. If instead we take the photons and we bin them up per time, we're just making a light curve. Now this is an X-ray light curve of a black hole, which is about 6,000 light years away, a black hole called Cygnus X1, and this is looked at with an X-ray satellite called NICER. And by binning up the photons that's coming to us and binning up over time, I'm making a light curve. So on the lower axis, the x-axis, I'm listing time. I'm binning things up in 1 second. And on the right axis is essentially a normalized version of the number of photons. And I've done this, so I've made an average of 1. This is so I've taken out the total number because that's not really important. What is important in this particular case is the fact that you see this going up and down. That is not noise in our detector. That's really happening in this particular X-ray source, that you can see it going up and down by roughly 20, 30, 40% in the time scale of a second. Now, because X-rays are very energetic and I can count how many we have here, I can tell you that in that 1 second bin there, that's not noise, that's a real fluctuation. That is essentially the equivalent of 100,000 suns turning on in the X-ray in the span of 1 second. So that is basically saying that this is a very compact object to have something that can turn on 100,000 suns in 1 second. Now, you know that nothing can move faster than the speed of light. So to give you an idea of the size scale, our sun is 3 light seconds across. So this has to be happening in something that is significantly smaller than the size of our sun, that we have 100,000 suns turning on in X-rays in only 1 second. So that's a light curve, but we're not going to really talk about too much about light curves. Although we can, if we wanted to, we could bin over both position on the sky and time, and that would be a movie. And we have done that with the Chandra X-ray Observatory. And this is a movie of the Crab Nebula. This is done over several observations taken over about a decade or so. And you can see sort of these ripples happening in the nebula around the pulsar in X-rays. Yes, it's about, this is about 10 years, I believe. So roughly once a year. The scale on that is, on the sky, it is about 20 arc seconds or so. That is about 1/100th the size of the moon, or so. Now, what this talk will be about is when we instead bin up the photons over energy, and that's called the spectrum. And here's an example of a neutron star of a spectrum, and what we plot along the x-axis is the energy of the photons, and on the y-axis we plot some measure of the counts of the numbers of the photons. And I'll be unfortunately using a lot of different units, but don't worry too much about that. Just know that that's a sign of the brightness at a given energy, and you can see in this particular case that there is a spike there at an energy of 6.4 kilo electron volts. And that is a spectroscopic line. Now that is from iron. And a lot of what I'm going to be talking about today is specific measurements of specific materials emitting X-ray light at well-known understood energies. And that's why they're useful, because we understand atomic physics well enough to know what these energies should be. And by measuring these energies, we can identify species in the material. We can identify velocities. We can identify temperatures and densities. For this particular line of iron, what this is basically iron has a lot of electrons in it, and they're each in different quantum shells. And this is a line where an X-ray comes in and knocks out the innermost electron of the iron, sends that off to infinity, essentially. It ionizes the iron, and then you have a cascade of electrons going to lower energies. And the last transition that happens is from the second energetic shell to the first. That what we call a 2-to-1 transition happens at an energy of 6.4 kilo electron volts. And that's a very characteristic energy there. That width of that line that you see there is not due to the intrinsic width of the line, but instead is due to what our detectors can do. So this is a charge coupled device, a CCD detector, kind of like in the back of your cell phone. That's the best we can do. I'm going to be talking today about current detectors and future detectors that can do a better job on measuring these properties. Now, I'm going to give you a little bit more math, and this will be kind of the end of the math today, just to have an idea of where these widths are coming from. And we'll talk a little about statistics. I said, astronomy is really simple. It's just a matter of counting photons and putting them in bins and histogramming up either by position, energy, or time. And anytime we do counting of something, there's a statistic involved with that. If you expect to get 10, you don't always get 10. And this is a plot. If I expect to get 10 photons, what am I going to really measure? Well, I can measure anywhere from 0 to 20-ish photons. And that's the distribution of the fraction of the time I'm going to get between 0 and 20 photons. You can see there's a spread of that. And that's called Poisson statistics or counting statistics. If I instead expect to measure 100, you see it's much more clustered around 100. If I expect to see 1,000, it's more clustered around 1,000 still. If I expect to see 10,000, it's much more narrowly. If I expect to see 100,000, it's much more narrowly clustered about how accurately I measure. The error I get in counting something goes as 1 over the square root of the number of things I'm counting. So the more photons I can gather, the more accurate I can say the total number of photons I'm going to have and understand, which is why we always want to make our detectors as big as possible so we can up that number of photons. But this is not only true for the number of photons that we expect to find, but when measuring the properties, we also essentially do counting statistics as well, and that's what affects the width that we see for these features. And that comes from these charge-coupled devices. These charge-coupled, these CCDs, like in your cell phone, these are semiconductors. They work by the photoelectric effect. Essentially what happens is in the semiconductors that a photon comes in, interacts with the material in what's called the valence band of that material, and knocks out an electron from the valence band to what we call the conduction band, and allows that electron to move in the material. And there's an energy gap for doing this. Now that would be, the physics of this would be a talk by one of the condensed matter professors here, like Eric Henriksen or Kato Murch or the like, could give you a Saturday morning lecture on the physics of these. But just know that this is a quantum device, that there's this valence band with the material in it that has electrons in it, photons come in, they have to go over a quantum energy gap to go to this conduction band, where we then count the number of electrons to determine the energy of the photon. The higher the energy of the photon, the more electrons we get. And what we do is we apply a voltage to this semiconductor, and we take these accumulated charges and we move them across the CCD to a place where we read out and we count those number of photons, and the counting of that photons leads to what we say the energy of that photon was. And again, there's a statistical uncertainty in counting that. This energy gap that we have to go across is about 1 electron volt or so. So if we have an X-ray with 1 kiloelectron volt, we're going to get about 1,000 electrons out of that. But the error on that is going to be the square root of 1,000 or so. So about, 35-ish. So we're going to have 1,000 plus or minus a few times 35, and that is going to be the uncertainty on our measurement of the energy of that photon, which leads to that width that you saw on the line there. That width is about 100 to 200 electron volts if the measurement is at 6.4 kiloelectron volts. So that's where the uncertainty in measurement comes. But we're going to talk about things that do that a little bit better. Now, here are some current X-ray missions, and pretty much all of these, at least at some level, work with CCD detectors where you're measuring things to order of a few hundred EV if you're for a KeV X-ray. The one that I'm going to be talking most about is the Chandra X-ray Observatory in the upper left-hand corner. It has great spatial resolution. It has really great spectral resolution. I'm going to describe that in a moment, but it has a very small area. There's other ones that sacrifice a little things like the energy resolution for having a bigger effective area or a wider bandpass. There's one there, Swift, that's designed to very rapidly swing across the sky and get onto things within only a few hours or possibly in some cases minutes. That was designed to chase after things known as gamma ray bursts. Neutron stars colliding with each other that emit bursts of gamma ray radiation. You want to get there very quickly when you find them. The one in the lower right-hand corner, you saw a light curve from that. That's the nicer instrument. That's aboard the space station. That one sacrifices spatial resolution. It has no spatial resolution whatsoever, and sacrifices energy resolution for superb timing resolution and very big area. So that's why we were able to do this light curve in bins as short as 1 second and say that that 1 second jump was all the source and not the statistics, because it's designed to be able to do things like that. So we're greedy. We would love to have everything. We would love to have large size, as many photons as we can possibly get. We would love to have great spatial resolution. This is extremely difficult in the X-rays. It's easy to look at yourself in the mirror in the morning. Well, maybe not for all of us, depending on how we're feeling that day. But optical light can bounce off of a mirror very easily. That's very tough to do with X-rays. We would love to have great timing resolution. That is tough to do with these charge-coupled devices, these CCD detectors. As I said, we have to apply these voltages and physically move the electrons across the chip before we read them out. So for a lot of these detectors, it literally takes a few seconds to read out the electric charge, and that limits the time resolution of these devices. And we would love to have great energy resolution. Silicon detectors, these CCDs, have been the most common, but there are other technologies which can do better, and we're going to talk about those. So we're going to start off with Chandra, and Chandra is designed to do great spatial resolution with great energy resolution, although not always together, and you're going to see that in a moment. We're then going to talk about this satellite called XRISM, which is designed to have large area and great energy resolution with a little bit of spatial resolution at what we call high energy X-ray energies. This will be launched in the fall. And then we're going to end off talking about Arcus, which is designed to have large size and great energy resolution at low X-ray energies. I'm wearing my Arcus t-shirt today. We will be submitting the proposal for this in October, and then we will find out, hopefully within about 2 years, whether NASA is going to give us the money to build it. So let's start off with Chandra. Chandra is the largest satellite ever flown on the space shuttle. It's about the size of Moss. It is about 5 tons. Its opening is about 6 feet across, and this is a cartoon of it. However, this is a real photograph of it sitting in the bay of the space shuttle. You can see there's about 2 inches left in the bay. It really was as big as could possibly be fit into the space shuttle. One of the reasons why it had to be so big is because of the difficulty of focusing X-rays, and we're going to talk about that in a moment. So as far as its abilities, it has the best imaging of any X-ray satellite ever flown. It can do 1 arc second on the sky, which is about 1/2000th the size of the moon. So if you hold out your arm and hold out your thumb in front of your arm and close one eye, that's about the size of the moon typically. Your thumb will pretty much cover the moon. So divide your thumb across by a factor of 2,000, and that's what we can do with Chandra. We have decent energy range ranging from about 400 electron volts to 10 kilo electron volts, or equivalently 4 million degrees to 100 million degrees. And when we use this one detector on this, the energy resolution we get is between 1400 and 200. The idea that energy divided by that width, we can measure this energy to be about 1,000 or so. That is great for X-rays. It's not as good as we can do in radio or in optical. Radio telescopes or the Hubble Space Telescope can do about 20,000 or so. And the other interesting thing that we do is that it does the widest range from faint to bright sources of any satellite in any wavelength that has ever been flown. It can see 10 orders of magnitude in terms of the range of brightnesses of sources on the sky. We measure single photons coming in at a time to very bright sources. So in terms of astronomical magnitudes, for those that know, it takes 5 astronomical magnitudes to make a factor of 100. So this is 25 magnitudes on the sky. So if this were the Hubble telescope, it would be like going from things that you can see in the visible sky with your eyes to the faintest things that Hubble has ever seen. That's the kind of things that this does in the X-ray. So its mirrors have to be a little bit different than mirrors for an optical telescope. So rather than being face on, because I said the material X-ray wavelengths are shorter than the spacing of atoms in the material. So if you were face on, and for those online, if you can see my hand, if you're looking through my hand face on, you can see it through my fingers. But if I were to tilt my hand towards the side, my fingers start getting closer together, you don't see the gaps between my fingers. So basically, we have to take a mirror. If it were face on, the X-rays would penetrate through and be absorbed in the back of the mirror. But if we tilt the mirror on the side, the atoms look like they're spaced very closely together, and the X-rays can reflect off of it. So that's why we have to, as you see here, we have to take our mirrors, tilt them on the edge, and we do it actually with 2 sets of mirrors. Because if we only did 1 set of mirror, the focal length would be very, very far away. Rather than being 40 feet, it would be 100 feet. So the second set of mirrors are there to do a second focusing to make it a little bit shorter of a focal wavelength. So rather than having 100 feet focal length, we can get away with a few tens of feet focal length. But because if we're taking our mirrors and tilting them on the side, we are sacrificing effective area. That, you know, there's a lot more area if you're looking face on versus putting the mirror side on, but to get the reflections, we have to put the mirrors side on. The other thing that we have to do is, because the wavelength of light is so short, we have to make these mirrors very, very smooth and uniform. And that is where the difficulty is. So these mirrors actually are much smoother and much more uniform than the Hubble mirrors. But Hubble's very long wavelength. So there can be some wiggles and deformations in the Hubble mirrors. Optical light doesn't care. Is the question back? It does make a real image, and you're going to see that. So that Crab Nebula was with these Chandra mirrors. The image is better on the center and does get distorted as you get further away from the center. And you're going to see that in a moment. No, it's a great question. So what are the mirrors? The mirrors are very thin glass with a coating of iridium on them. But typically you use a very dense metal to coat this. So X-ray mirrors are either coated with something like iridium or gold. And you try to make them as thin as possible because weight is money when you launch something into space. And that's really the difficulty in making these mirrors, is that if you start to make them bigger, they would start to distort under their own weight. And that's the tricky part. So these were made basically as big as they could be made. So this is an image of the Orion star cluster. If you've gone out at night and looked at the sword of Orion and seen the fuzzy middle star, this is the star cluster in that fuzzy middle star of Orion. This was done with the Rosat satellite in the early 1990s. This was the best X-ray imaging we could do. And this is what we can do with Chandra. And that's our image of Orion there. You can see it's much better. That's about the size of the image is about half the size of the moon. That streak there is because of the reading out of the CCD. You're trailing electrons along as you're reading out for the brightest sources. So that's really a distortion. And if you look carefully, you can see that the stars in the middle look more like points, and the stars around the ring on the outside look more like ellipses. That's the distortion of the mirror. So you can absolutely, definitely see that. There's a new set of detector mirrors being developed right now for a proposal, one of them competing with us in Arcus, to try to make something that is more uniform across the whole field. And it's a tricky thing to do. So that's the Orion star cluster. Yeah. We'll get to what's basically learned is that you can separate all these into
can you repeat the question, please?
Yeah, the question, what was learned by the imaging? And what is learned is that the Orion star cluster is essentially a set of stars with all of the same birth date, more or less. And so you have a whole population of stars of different masses here with essentially the same birth date. So you've got this measurement of the activity of young stars, and you can do it as a function of mass. And we're going to talk a little bit about more of that in a minute. I believe this is the central star of the belt, the cluster of the belt.
The question,
not the belt, the sword. Sorry, yeah, thank you. The question is this M42? Is this what? This is the middle. This cluster, I believe, is that fuzzy patch on the scabbard of Orion.
What about John Tucker? You are John Tucker?
Yeah. Yeah, so the question in the audience is, when does this come from? These stars, I believe, are a few 100 million years old.
Yeah,
so this is
from Washington University. That's why I was late.
Please mute in the background if you're.
So
this is the Cassiopeia A supernova remnant, and this was done with the Rosat telescope. again back in the 90s, and this is our image of it in the X-rays, and you can see it's much better. If you look very closely, you can see a pale blue dot in the middle. That is the central neutron star that's left over after the supernova explosion. It's the first time it's been able to be spatially resolved. And the material around it is the hot gas. The colors here represent the energy resolution of the CCD. So we can do some interesting things with the energy resolution of the CCD in this particular case. And that tells us things like temperatures, densities, and composition of this material. So most of what you see there, if it's blue, it's iron. If it's green, it's sulfur and silicon. And if it's red, it's carbon, nitrogen, and oxygen. But we're going to do a little bit of a better job of that in a moment. So we have something else aboard Chandra, and it's called these transmission gratings. Transmission gratings are basically prisms, but prisms for the X-rays. They're small, thin sheets of gold with grooves in them, and we pass the X-rays through these grooves. And when you do that, and you can either pass through or reflect off grooves, and you create basically little wave fronts as you go through these grooves, and these wave fronts then propagate out as these spherical wave fronts, and they interfere with each other. And in some places, they null out, they destructively interfere and leave nothing, and in certain specific locations, they constructively interfere, and that happens as a function of distance perpendicular, and that takes out a specific wavelength. So you take the X-rays and spread them out into a line where each position along that line is a specific wavelength or energy. And that's called it's essentially just, it's acting like a prism in this particular case. And we have 4 sets of mirror shells. So we have 4 rings of these gratings going around. We swing these gratings in front of the mirror, and then we create this diffraction pattern on our detectors, which kind of looks like this. Don't worry too much about the math up there, other than just to note that the distance from the center that you go is going to be proportional to the wavelength. So short, and there's these 2 sets of these detectors, short wavelengths, high energy is going to be towards the center, and long wavelengths are going to be towards the outside. And at a specific spot, you get very specific wavelengths. And they come in what we call orders. At any given specific spot, you get a specific wavelength, or half that wavelength, or 1/3 that wavelength, or 1/4 that wavelength. Or equivalently, you get a specific energy, or twice that energy, or 3 times that energy. And it's designed so that these 2 sets of gratings lined up with each other do a wavelength and half that wavelength. And we're going to show you what this looks like in real life. The more you can spread this out, the better you can measure the wavelength. So basically, it's the physical size of your CCDs determines how well you can measure a wavelength. This is what it looks like. These grooves are about 100 nanometers apart. As I said, we have 4 mirror shells. We have 4 sets of these that we swing on. And I have actually brought some of these. So I'm going to pass this around. This is one of the facets. There are about 400 of these on the detector. You can see from the audience here that if you're looking at this, you're looking like you're reflecting off a solid surface of the gold, but it's when you get it, hold it up to your eye, you'll see that you can actually see through it. This was a going away gift for me when I left. Each one of these facets cost about $20,000 back in the day, and there was 400 of them. And of course, the number is that if you made 400 or 500, it was going to be the same amount of money. It was really the technology to develop that. So I'm going to pass that around. Feel free to look at that. You're looking at a $20,000 artifact from when Chandra was launched 20 years ago. So this is the Orion star cluster done with the mirrors and done with just our CCDs, but put the gratings in and zoom in on the center, and we get that instead. Now, this is done over many different observations. So the reason why it looks like a swirly pattern is that this was taken over many months, and the spacecraft is rotating on the sky, so the position of the gratings are changing over time, and you're seeing that there. Now, here you asked, what do we learn from this? One of the things, because these are young, when we do the gratings, we can learn a little bit about stellar history. Now, we would love to go and do spectroscopy of the sun with time, but we can't go back 5.5 billion, 6 billion years to do the history of the sun. However, we can go out and look at other objects in the sky about the mass of our sun, and these are 3 different objects looked at with the gratings, 3 different stars, all about the mass of the sun, but at different ages. The top one is 100 million years old. The middle one is 300 million years old. And then the bottom one is about 6 billion years old, like our sun. And this is a spectrum. And just to kind of orient you, energy goes along the x-axis. So higher energy is to the left, lower energy is to the right. And age is going from youngest to oldest. And each of those lines that you see there is a different element seen in the spectrum. And so you can see that we have some neon in there. We have iron, we have oxygen, we have magnesium. For the most part, you see these Roman numerals there. That tells you how many electrons were knocked off of this. So neon has 11, we're going to get this right. When we say neon 10, we have knocked off all the electrons except for one of them. So this is neon that's kind of like hydrogen. So it's got the core of neon, but it's only got one electron going around it like hydrogen does. Magnesium, there you see magnesium 11 and magnesium 12. Magnesium 11 is like helium. So it's got the core of magnesium in its nucleus, but it has 2 electrons going around it. Magnesium 12, again, has the core of magnesium, but has 1 electron going around it, like hydrogen. And we understand the physics of these very well. Now, we've knocked off most of the electrons because we're being bathed in X-rays, and the X-rays are doing a very good job of ionizing all the material. But it's actually kind of nice because they're making them simpler, like helium and hydrogen. We understand the spectroscopy better, and we can see these energy levels like we see in hydrogen in this particular case. So we can measure the properties. So we can measure the compositions. By seeing the shifting of these lines, we can measure velocities. By measuring the intensities of these lines, we can measure densities and temperatures. Now, something that you should be able to see by eye here. Now, who can actually look at this? What looks different from the top to the bottom? Actually, 2 things should look different. Go for it. We had someone in the audience, so you see some of the differences.
Can't understand.
Yeah,
exactly.
No, I was looking at this.
So you can see in the top one, in the top, there's many more lines. In the bottom, there's many fewer lines. In the top, more of the lines are to the left. As we go to the bottom, fewer of the lines are to the left. What few lines there are to the right. And basically what you're seeing is both the activity in the X-rays is decreasing with age, and the characteristic temperature of the X-rays is also decreasing with age. So young stars are very X-ray active. So all the solar flaring that happens is more intense in young stars, and that goes away with time. This is probably a good thing. So this is actually something that we want to understand is, under what conditions do young stars sterilize planets in their solar system due to early X-ray activity? Conversely, however, early X-ray activity might be important for planet formation. You might need to heavily ionize the protoplanetary disk in order for it to coalesce together. There's instabilities that we expect to happen in disk, and it might be necessary for X-rays to exist in the early universe, in the early solar systems, to ionize the disks so they can actually clump together as planets. But then you don't want too much of this to then sterilize life. So that's the things, kind of the things that we're studying, is trying to understand. We can't go back and look at our solar system and understand its early history, but we can look at other stars like our sun and understand the history of things that were happening. So yeah, the question is, we put our sun back 4 billion years. Would it look like the top? Yes, it should. As far as we understand, it should look very much the same. That we expected our sun to be much more active in the X-rays and more solar flares in its early life. So now we're going to look at a black hole in the X-rays. This is the black hole Cygnus X1. I showed you a light curve of that earlier. You can see there, again, the stuff you see in the middle of that streak and that black hole is not really the black hole in it. That's properties of the CCD. But if you can see it, actually that faint red circle around, that is actually real. That is dust in front of Cygnus X1. That's like if you look at a cloudy night in front of the moon, you might see a halo around the moon. That's exactly the same thing here, except for this is X-rays. And then you see that we're spreading out the light in X-rays, and we have 100 million degree light towards the center, and we have 10 million degree light towards the sides. Now, for this particular case, Cygnus X1 is in a binary system. This is a sketch of that binary system to a relative scale. On the left is the size of the companion star that is donating material to the black hole. That's not really the size of the black hole to scale, but the separation between the black hole and the star is to scale. The colors around that are what our models say the atmosphere of the star should look like. So we're seeing denser atmosphere closer to the star, less dense atmosphere away from the star, and it's going to be as a function of the orbit. Those lines there are our line of sight as the two stars orbit around each other. So I've made this picture so we're looking always at the same edge on of the system. So our line of sight is varying through the atmosphere. So sometimes we're looking through very dense atmosphere, sometimes we're looking through less dense atmosphere, and we can use the X-rays to kind of separate that out. And this is what we see in the light curve. So again, we're now on the right, we're showing that same view. Each of those little hatch marks there are different observations with Chandra. On the left, we see a light curve as a function of that orbital phase. And we are seeing now the spectrum that we measure with these gratings, and we're seeing all this absorption. So in this case, we're using the X-rays from the black hole to X-ray the atmosphere of the companion star, so we can learn about the structure of actually the atmosphere of the companion star. And we're seeing all sorts of absorption here from silicon and magnesium, and we're seeing that change as a function of the density. In fact, a fun, interesting fact, a lot of these wavelengths were very difficult to measure in the laboratory until fairly recently. The astrophysical observations were actually the most accurate measurements of these X-ray wavelengths until about the past 10 years or so. We've only been able to catch up in the laboratory. It's hard to make an X-ray source that you can measure that accurately. But here's another case of another black hole where we are looking at winds being blown off of the material falling onto the black hole. This is a black hole known as GRJ1655-40, and we looked at it with the gratings, and here's the spectrum here. You can see this is measured in wavelength, so this is about 2 kiloelectron volts or 20 million degrees. The red line is where we expect the lines to be. The blue line is where the lines were actually measured, and you can see they are shifted from one another, which basically means all that material is flying towards us at 1,500 kilometers per second. And by measuring the strength of these lines and the velocity of these lines, we can tell the pressure, density, and velocities, and we can say that these lines aren't being blown off by the radiation of the black hole. Specifically, they're happening too close into the black hole. What we think is happening is that the magnetic field's being twisted up on the material falling in to the black hole is driving a magnetic wind away from the black hole at very high velocities. And we're going to end off with the Chandra observations with this supernova remnant, EO102. It's about 200,000 light years away. This is what EO102 looks like with our CCDs. But if we put the gratings in, this is why we care about supernova remnants. Supernova, like Carl Sagan used to love to say, you and I are made of star stuff. That was one of his big lines. So where does the material in our body come from? About 10% of us comes from the Big Bang. That's the hydrogen in our bodies is all the Big Bang. 90% of us is coming from supernovae. The carbon, nitrogen, and oxygen had to come from stars being blown up, spreading that material out to the galaxy, and then newer, later star systems. Is a 1% of us. The gold, we do have some gold and platinum in our bodies. That comes actually from neutron stars merging together. These gravitational wave events. So we're made up of exotic stuff. 10%, you're 10% Big Bang, 90% supernovae, and 1% colliding neutron stars is what you are. So that's why we actually want to study supernovae, to understand the 90% of us. And we can do that with Chandra, put the gratings in, we can spread that image out into the discrete lines of the material there. We can also get an idea of the velocities. Because we have this image, and again, you saw before that we're sending this image in two different directions. If all the velocities in this image were exactly the same, the image on the left would be the same as the image on the right. But there's different velocities on different parts of the supernova, so we see those blue shifted and red shifted and distorted. But everything, again, high energies are always going towards the center, low energies are going towards the outside, so the image is distorted on the left differently than the image is distorted on the right. And so comparing those distortions gives you a map of the different velocities in this image. But here you can see where the limits of what we call dispersive spectroscopy are kind of hitting. We need to look at point sources like Orion, or we need to look at sources like this EO102 that are small compared to our field of view with very well-defined structures. Gratings, because they're spreading by wavelength, work best at low energy X-rays, less than about 2 kiloelectron volts. But there's lots of interesting things out there with wide fields of view and lines at higher energies, like that 6.4 keV line we saw in iron. So bigger supernova remnants we care about. Clusters of galaxies we care about. So what we're going to do in the fall is launch what's called an X-ray calorimeter. And that's going to be the XRISM instrument. So rather than dispersing the photons, we basically are going to have these thermal detectors. Basically, keep your detector very cold, and you have essentially this little thermal bath in there. X-ray photon comes in, heats up your detector, and you measure that temperature change. And then that temperature change that you measure is proportional to the energy of your photon. And you do this by basically making these quantum detectors where you're running power through it. It's got some heat capacitance to it. It's got a thermocouple to cryogen to keep it cold. And X-ray photon comes in, raises the temperature, and then that temperature decays way back to its equilibrium temperature again, because it's in coupling with that bath. And you measure these little pulses of temperature rises. And you get a very accurate measurement of the energy of your X-ray. That gratings work by measuring constant wavelength. Calorimeters work by measuring constant energy change. So gratings are great at low energy where wavelengths are long. Calorimeters are better at high energy where wavelengths are short, but you want that constant energy resolution instead. And that is going to be essentially what the XRISM detector is going to do. Is going to launch in the fall. Here's the diagram of what this looks like. It's going to have these calorimeters on board this. These calorimeters are this set of 6 by 6 pixels. So we have 36 pixels on the sky. That's not a lot, but still it's very impressive given the fact that we're going to have 5 EV resolution which basically means at this 6.4 keV line, we're going to have about 1200 resolution elements in the spectrum. Now, this is a replacement for prior attempts. I'm going to show you spectra from these prior attempts. XRISM is a replacement for this mission, which was called Hitomi. Hitomi was launched a few years ago, but they lost attitude control, and they accidentally spun up the spacecraft and spun off the solar sails, the solar panels from the spacecraft, and it was lost after a few weeks in orbit. Hitomi itself was a replacement for an instrument called Suzaku. Suzaku had a calorimeter on it, but they had a venting issue with their cryogen, and they lost all their cryogen. It was still a very successful mission with its remaining CCD detectors, ran for 10 years, but it was supposed to do these calorimeter measurements instead. Suzaku was first called Astro E2 because Astro E1, which was identical to Suzaku, unfortunately did what they call failed to achieve orbit. It was kind of like a parabola. It went up and it went down into the ocean, and that was the end of it. So this is the fourth time we were trying to get calorimeters in the sky, and hopefully the fourth time will work. But it's tough. Satellite accidents happen, unfortunately. So what did Hitomi do? Hitomi had one great observation before it failed. It looked at the central black hole and gas in a galaxy cluster. This is important because black holes feed back energy to the material around them via winds, like we saw in GRJ 1655, and via jets. That energy comes back and affects all the surrounding galaxies and all the surrounding gas. So we can use these line diagnostics to learn about densities, temperatures, and velocities, and the composition of this material. But X-ray clusters are big, diffuse, and very hot, so we want the spatial resolution and the high energy X-ray spectroscopy if we can get it. And so this is an image from Chandra in the background of a galaxy cluster, and on top of this is the Hitomi field of view with the pixels kind of added up into different regions to give you an idea of what you can measure. And you can see they've made a little bit of a map there of the velocities they've measured and some of the temperatures they've measured. And this is what the spectrum looks like in that particular. That is that iron line there. It's a little hard to see, but if you look around the iron line, you see this faint red dot there. That's the resolution that you can get with the CCDs. But the calorimeter is the bright white line, actually set of lines there in the middle there. That line there in the red is actually multiple lines. This is iron that is like helium. And because it's like helium, it's got two electrons. So it's not only just one transition from this 2 to 1 shell, there's these different what we call angular momentum states associated with the electrons, the spin of the electron, the orbital angular momentum of the electrons around that. And each of these different angular momentum states have a slightly different energy. That all look like one line to the CCDs, but to the calorimeter, you can break that up into essentially what's 5 different lines associated with this well understood atomic physics. Gives us much more precise measurements of the temperature and densities by looking at the ratios of these different lines.
Good.
So we'll go. So the next one down the line, since we're getting towards the end of the hour, is what we're going to do is proposing this mission called Arcus. Is what NASA calls a probe class mission, $1 billion if they give it to us. It's in response to NASA said, we want to see probes in infrared or X-rays. $1 billion might seem like a lot, but keep in mind that James Webb is $10 billion. The next infrared satellite to be launched, the Roman satellite, is $4 billion. So $1 billion is actually what NASA calls a new cheap version. So prior to this call, NASA satellites came in 2 varieties. $400 million, which a lot of the other things, like NICER was a $300 million mission. And so the other things I showed you, a $300 million mission, or $4 to $10 billion like Roman and James Webb. So this new $1 billion class is kind of like this mid-range mission. So what we're proposing to do is low energy X-ray and UV spectroscopy, and to answer these questions. What powers black hole winds that can impact entire galaxies and clusters? How does matter cycle in and out of galaxies? How do stars in circumstellar disks form, evolve, and die? And 70% of the program will be driven by the community, whatever they want to do with it. Now for, yeah. Yeah.
Engineering all the way out to successful launch and beginning to operate.
Yeah, so the question is, of the $1 billion, is how much is it for the engineering versus to get it to successful launch? About 90% of it. Of the $1 billion, if this happens, it will be 3 months of my salary for 10 years. That's about it. And that does not anywhere come near $1 billion. Most of it will be going to Northrop Grumman and other builders to put this kind of together. This does not include the launch of the launch vehicle is completely separate. So it's actual one, it's the detectors and the engineering and the spacecraft. The length of time to launch will be, I believe, 8 years if it happens. Is $300 million missions length of time is 4 years to launch faster. And as we all know, James Webb took about 20 years to launch. Likewise, Chandra, back in the day, was $2 billion, took about 20 years to launch. So in terms of the science, these are two different simulations of evolution of clusters and galaxies in the early universe, with two different sets of assumptions about how matter gravitationally collapses. On the left, it's what we call an adiabatic approximation. It's not putting in a lot of the detailed physics. On the right, it's a lot of detailed physics of the feedback from black holes and supernovae affecting that. And you can see all the gas in between galaxies can look very different depending upon what assumptions you make about what's going on in the early universe. Now, this is what we're looking at for Arcus, is trying to probe that gas in between galaxies. One of the big missions that we plan on doing that. So, you know, if you've kept up with cosmology, the composition of the universe is about 70% of the universe is dark energy that we don't understand. 25% is dark matter that we don't understand. 5% is the baryons, the normal everyday matter that makes up. But what you might not know about the baryons, of this 5%, 90% of it's missing. Only 10% of that 5% is in things like stars and planets and interstellar material. Most of it is residing, we think, in the intergalactic medium and has not really been observed yet. So our job with Arcus is to use UV and X-ray spectroscopy to probe that. And the idea being that we're going to use these new silicon mirrors, which are called silicon pore optics. These, again, are going to be mirrors lying on their side with better versions of these transmission gratings compared to Chandra. The combination of these two is where Chandra, we had a resolution of 1,000, we're going to get this up to 2,500. And we're going to do it with 10 to 100 times the area. And then we're going to use, and that's a little bit of a sketch of what the spacecraft looks like, we're going to use background active galactic nuclei to shine X-rays through the intergalactic and what we call the circumgalactic medium and look for the absorption of these X-rays to characterize the properties of that gas. And that's what our mission is going to be. So I'm going to end off there, and just to summarize, spectroscopy allows us to measure the compositions, temperatures, densities, and velocities of material. X-ray spectroscopy is especially important because it characterizes the hottest and most energetic baryons. A lot of these baryons are missing, but it's an important part of cosmological history. And we have a current satellite, Chandra. We have a soon-to-be-launched satellite, XRISM, and hopefully Arcus one day that will be contributing to this story. So I will end there and start taking questions. So. The question is, does dark matter go faster than speed of light? No, can't image it. No. The problem is that dark matter doesn't interact with anything other than gravitationally. That's the big problem, is that we don't know. Gravity can't go. So yeah, gravity can't go faster than the speed of light. But the only thing that we found that dark matter interacts with is gravitational. So it bends light, and we can see that bending of light in especially a lot of these images. We can see that happening. But we've been looking for other signatures, like if dark matter annihilates with itself, it possibly would emit X-rays. So there have been people who've been looking for X-ray signatures, like an X-ray line that we could associate with dark matter. There's been also, in clusters of galaxies, there's the possibility that dark matter could absorb X-rays. So people have been looking at clusters. Some of the best limits on dark matter models have been looking at that central active galactic nuclei in a cluster and putting limits on unexplained absorption lines to say that could be dark matter in the cluster. But that's the problem, is that we don't have a good theory, so we don't know exactly what we're looking for. We just know the kinds of things that could happen, and we haven't found anything along those lines yet. Yeah, the question is, how can the expansion of the universe happen faster than the speed of light? That's only really from our perspective. No two places are really kind of going apart. The speed of light is something that really is it's a local measurement, and what's going to happen is as things get further away and effectively are expanding away from us, what appears to be faster than the speed of light, that part of the universe disappears from our view. So it basically drops out from our view because no, the universe can go. It can go. So it's like the question is there a limit to the speed of the effective speed of the expansion of the universe? And the answer is no. It's like blowing up the surface of a balloon. It's like the analogy of what I was at. Locally, you can only see what's happening at the speed of light, but globally, the balloon could be expanding everywhere, and that's fine. That means that some parts of the balloon are eventually going to go beyond your ability to see them. So in some sense, we're almost seeing as much of the universe now as we're ever going to see, because as the expansion of the universe accelerates, more and more of the universe is going to drop out from our view.
What a shithole you are, man. You are a shithole.
Oh, hold on 1 second. We got a Yeah, so the question is, can we do spectroscopy of planets? And the answer is yes. It will mostly be done in the infrared. James Webb will be doing that, but that is at least part of the Arcus program, is to do spectroscopy of planets. It's tougher because there's fewer X-rays and our detectors are smaller. But it is definitely something that we've thought about and that we will try. Question in the back of the room here. The question is, the atmosphere does block, what blocks X-rays? Can you do X-ray astronomy in the ground? The atmosphere does do a very good job of blocking X-rays. It's the oxygen, nitrogen and is sufficient. It doesn't take a lot of density to really block X-rays. You know that when you have a dental X-ray, yes, the dentist does run out of the room and puts the lead vest on, but when they put that X-ray detector up to your face, they pretty much have to put it right on your cheek because it only takes about 10 centimeters or so for that. So yeah, we do have to fly all of our X-ray satellites as much as possible above the atmosphere. You can do it with small rockets to get the detector up for 15 minutes. It has been done on balloons where you get it above like 95% of the atmosphere, and that gets you a lot. So you have to go pretty high up to get above enough the atmosphere. But from the ground, no, pretty much you can't. The ground is it's really mostly the visible and the like. Let's see, is Ann Miller, some question, what will we do with knowing what we are made of? How can we best use that knowledge? Wow, it's always a philosophical question. It's kind of good to know. We don't really understand what it takes to form solar systems and form stars. You know, the history of early stars have less what we call metals, and to an astronomer, a metal is anything that's above helium. And we don't know what's quite required to make planets. So we don't know really the conditions that were necessary for us to get here. We do know that it's very unlikely that solar systems were formed in the first generation of stars because there weren't the metals to cool the material and make that. So that's part of what we want to kind of learn is how things changed over cosmic time. What were the properties of solar systems and stars, early universe to now? We know at least 6 billion years ago, things were good enough to make us. We don't know if that's common or rare and how that changes as time goes forward. I think another question. Oh, what was this first detection? The first detection of X-rays were rocket flights, late 60s, early 70s. And then there were early satellites. So Cygnus X1 was detected around 1970 in the X-rays, and it was fairly quickly decided that it was likely to be a black hole based upon the brightness of the X-rays and, again, the rapid variability of the X-rays. So, yeah, that was from rocket flights. So the earliest things were rocket flights, and they were doing things in the 2 to 10 kilo electron volt range. But Cygnus X1 is so bright that was relatively easy to see with a fairly small detector. And again, it's going up and down by 50% in 1 second, which is enough to tell you that it is very, very small. And so that was and then people looked in the optical and looked at the orbital properties of this optical star and determined it had to be a fairly compact system. The whole system is revolving around itself on timescales of 5.5 days. So that gives you an idea that whatever's there is in a fairly small region. Yeah.
Where can I get a cool Arcus shirt?
Where can you get a cool? You can. I got this from. Yeah. Well, we will have these eventually. We ordered these from Land's End. And of course, since we ordered these from Land's End, I get emails every 2 days. Hey, would you like to order some more? And that's been going on. This is actually essentially our third attempt at doing Arcus. We had a $300 million version of Arcus a few years back, where we made it to what's called Phase A, where there was 2 of us, and we spent a year putting together a dog and pony show for NASA. And we did a big presentation and to say, this is our plans. And NASA came back with a review. Your science, excellent. Your science implementation, excellent. We think the other guys will be cheaper and less likely to cost overrun. And that was literally the review. We got like, it was about as good as you can do and still lose, unfortunately. And that was for the infrared folks. Right now, thanks for coming. there's 5 different proposals for X-rays for this probe class. So Arcus is spectroscopy. There's one called StrobeX, which is going to be devoted to timing, and will do very, very precise timing with very, very large effective area. There's one called HEXP, which will be essentially low energy gamma rays, doing imaging and spectroscopy with low CCD quality spectroscopy with low energy gamma rays. There's one called Axis, which will be doing very wide field imaging. And there's one called LEM, which will be doing what we call diffuse imaging, trying to image the faint gas around galaxies closest. So rather than measuring the gas via spectroscopy through absorption, they're trying to measure the gas via the emission. I think that's actually a harder thing to do. And at least that one, I would rather do it via Arcus. So there's 5 different good concepts out there for the X-rays. And there's another 4 in the infrared. NASA will pick 2 or 3 of them sometime next year. And you will do again, you'll have a year to go through the process and decide, here's our presentation to NASA, and then it will pick one sometime about 2 or 3 years from now. Then it'll be 10 years to get it built together and launched. How much of the missing baryons? Question online. Yes, okay, one, is there any gamma ray spectroscopy being proposed? The answer is 2 answers to that. HEXP is being proposed to do CCD quality gamma ray spectroscopy. Professor Henrik Krasinski here is working on calorimeter detector development. That will be further down the line to do gamma ray spectroscopy. The idea being to do very precise measurements of what we call annihilation lines. So electrons and positrons annihilating with each other and making a gamma ray line at 511 kiloelectron volts. So short term, there's CCD quality spectroscopy being proposed for gamma rays. Longer term, there is calorimetry being developed, and that would be more a 10-year time scale. Another question online is how much of the missing baryon matter is in black holes? Black holes could be some fraction of the dark matter. In terms of the baryonic matter, we know from what's called Big Bang nucleosynthesis that 5% of that material is in baryons. That is all in the normal universe. So it's in stars and gas. It's just a question of finding where all that gas is. And most of it, we believe, is in the intergalactic medium. And so we should be able to do a proper accounting of the 90% of the 5% that comes from Big Bang nucleosynthesis. So our models of cosmology tell us how many baryons there are. It's just a matter of doing the census of where it is in terms of developing galaxies, galaxy clusters, and stars. And that's really going to be, I think, determined over the next 10 to 20 years. Any other questions? Yeah. Well, the detectors are, silicon detectors, and they're kind of designed to absorb it, and it's the absorption that is releasing the electrons. So you want to absorb the X-rays. If you could absorb it and know the direction it came from, then you potentially could, do something with that. But it's hard to reflect, but yes, X-rays are hard to reflect, but easy to absorb. And determining their energy, you want to absorb it, so that's fine. And that the trick is that actually there's a lot of work going into reflection technology. Professor Manel Arando here is working on technology to make bigger versions of these reflecting mirrors. The tricky part is making them smooth. So the concept is you can make them big, they're going to be a little bit wrinkly, but you're going to put electrodes on the back, and then you're going to have the electrodes strain the material and smooth out the wrinkles. And do that in space. And so that's the most promising technology in the long term, to make big mirrors that you can make smooth enough to do good reflections. Basically, you have to correct them actively and you'll have to do it once they're flying in space. And so that's the goal. So a lot of technology development is trying to figure out how to put stresses and strains electronically on the glass to smooth it out and make bigger mirrors. Well, it's essentially, yeah, the question is it like, can you have adaptive optics? And the answer is that is the X-ray version of adaptive optics. Any other questions? If not, there's still some tours going on down the hall, and there might be some coffee left over there. So feel free, and thank you for coming.
Thank you for your talk. Thank you very much.
Yeah, thank you very much for coming online. Tours of the lab of Marty Israel, so the balloon experiments that have been working on the cosmic rays. So those are going on right now.
I enjoyed your talk. Let me ask you one other. I watched this television show, Mysteries of the Universe, that comes on. It has astrophysicists from New York, and they have it on a basic level where I'm a doctor, you can understand some of that. You know, when the Big Bang happened, it was a dark universe. When did photons or light, how was light created?
Oh, okay, yeah.
How was that created?
The question is, how was light created? Well, of course, the cosmic microwave background, because the universe was hot, there's thermal radiation, so black body radiation was in the early universe, and then as the first stars formed,
so it got the right wavelengths or frequencies to create light?
Yeah, so the earliest stars were probably very massive, very large, very hot.
Billions of times bigger than our sun.
Yeah, probably hundreds of times bigger. So yeah, so there was radiation from the Big Bang, the thermal radiation. It was hotter and shorter wavelength in the early universe, and then the first stars formed, probably fairly early, and that created ultraviolet and optical light, which then ionized the universe and made it more transparent. And then there was probably also a very early black hole. These stars probably blew up very quickly because they were very massive and turned into black holes. And those black holes merged, and then you had accretion onto the black hole. So turning on of jets, an active galactic nuclei via accretion onto the black holes probably happened much earlier than our models are comfortable with really figuring out. Yeah, they were happening. It started happening very, very quickly. So we were in what is called the third population of stars right now, and we can see the second population. The first population of stars was probably so rapid and so long ago that we can't see those. And
another question I had, you know, the Webb telescope it's phased away from the sun and it's working near absolute zero. Why do you have to have such cold temperatures? And I know you don't want interference from the sun, but to get images, it has to be
right. So okay, so right. The question is, why is the Webb telescope angled away from the sun and kept cold? Because it's working in the infrared, and any little bit of temperature of your spacecraft is going to emit infrared radiation. So you want to have as little local background from that as possible, and so you want to keep it very cold. And that's why they have these series of baffles to keep the light, keep the heating of the spacecraft to a minimum, so there's no glowing of anything nearby. No, this is why it's expensive. It's all these engineering questions that goes into it.
That's why I told you. So, you know, looking at the elements of these stars, but looking at elements and the signature on planets that we can see whether there's life. I mean, the question is, are we the only thing here? Well, the answer to that is, you know, statistically there's life everywhere. But being able to image those planets and see that there's a signature the same as we have here would be very important.
Yeah, I think there's, I'll say a 50-50 chance that in my lifetime, hopefully 30-ish years, that spectroscopically we will find a signature of a biosphere around another planet.
Sorry? Rare Earth. Yeah. No, I don't. It's a good book that talks about how common life is common, intelligent life that might be very rare.
Yeah.
You read that book?
Yeah, of course. Yeah, the book, The Rare Earth.
Library. Well, the other thing is whether there would be satellites around planets that would show intelligent life, making that distortion from the light from the planets by having satellites or whatever go around. And if you image that, then you have intelligent. You have information.
Yeah, I think finding evidence of intelligent life is going to be really, really tricky. I think, as I said, I give it 50-50 in my lifetime that we find spectroscopic evidence that there's a biosphere, that there's things like photosynthesis and respiration going on a planet. It will probably happen in the infrared. We do have plans to use the X-rays to at least characterize atmospheres of planets. I don't think we'll find, it's not really, X-rays are not designed for doing signatures of life, but they will give you information about atmospheres.
You know, if you look at the moons of Jupiter or whatever, and there's water underneath the surface, geysers, whether you can look at the signature or the chemicals, whether they're biologic signatures that are coming out even in our planetary system here, whether you know these imaging things could detect.
I think that
I think that we're going to find life, like intelligent life, but I think it's probably throughout our planetary system on these moons that have the right, have water and oxygen.
Yeah, I agree. So yeah,
Vents like at the bottom of our sea.
Right. I think the best chance for finding real solid evidence of life would be something like the moons of Saturn or the moons of Jupiter, probably underneath an ocean. I know there's always talk about
Mars a million years ago in an atmosphere and the stuff there that you know is panspermia. That may be part of what we're from. It's not Big Bang, but it's from Mars.
Yeah, I always the concept of that life started on Mars, then came to Earth via media. It just it seems to violate Occam's razor from my point of view. Is that if you can, let's form it on Mars and then transport it here. Why is Mars so much better for forming life that you want to take that extra step? Which is not to say that life didn't form on Mars, but I think the idea that you want to go there to invoke that, it just seems to violate Occam's razor that it's just one step too difficult.
And so forth, we're finding organic molecules, and so you know the bombardment of our Earth and the moon was spun off and so forth. Bombardment. You know, a lot of these asteroids and so forth have chemical signatures that can be spun into life. So, I mean, it may not come from Mars, but it's bombardment that, you know, 3 or 4 billion years ago could have had the chemicals here to start life.
Yeah, and actually, that's so the idea about having the chemicals for life in the solar system, and where did they come from? That's sort of like one of the indirect questions we want to do with the X-rays is understand what early stars look like from that point of view. To what extent does the X-ray activity of early stars potentially sterilize and destroy those molecules in early solar systems? So obviously the chemicals in our solar system survived. There's some people who believe that a better area for looking for planets in what's called the habitable zone would be these stars called M dwarfs, very low mass things. But to some extent, as we look at those more in the X-ray, some of the younger versions of that seem to be very X-ray active, maybe too much so for the chemicals associated with life to have survived.
So, you know, we had solar flares in 1850 or whatever, that the telegraph system ran backwards and so forth. you know, could we have a massive flare of the sun that would knock out your Chandra systems and the satellite systems, so we'd have a massive problem with communication and so forth from a major solar flare that happens maybe one every 200 or 300 years, but if we happen to be in the wrong time.
Yeah, no, so, okay, yeah, the question, if anyone's still online, is can a solar flare knock out a satellite? And the answer is yes. So there was a very big one, I think it was 1975, that missed the Skylab astronauts by a few. It would have given them a lethal dose. It would have been, and it would have been one of those things that they would have come back and died months later if they had been up there. The Chandra satellite can handle maybe 2 of those. It's possible, though, that one that large would knock it out. However, usually there's enough monitoring of the sun going on that you would see the event leading to the flare first and know that you had a few days to do something about it. And what you would do is you would shut down all the electronics in the satellite. You would move the detectors out of the way of the focal plane of the telescope as much as possible. And then you would turn the telescope as much as possible so that the thicker, less important parts were facing towards the flare and the more sensitive parts were facing away in the flare. So if you had enough warning, and you probably would, you would shut everything down and try to orient the telescope so you'd write it out as much as possible and restart it. So we do that a few times a year with some of the major asteroid storms that happened during the year, like the Perseids, that for a day you turned off the satellite and you oriented away from the direction that the meteors are coming.
Story Musgrove, who's the astronaut that spent more time in space than anybody else, and he's on the project, you know, to put people on Mars. And as you know, there's no magnetosphere there to protect people on Mars, so you get radiation all the time. And as a biologist, in a year, you'd have enough radiation that you'd have dementia and have neurologic symptoms. And trying to protect people, whether they go into these volcanic caves to protect them against radiation, the radiation exposure on Mars is going to be, I think, probably the major thing.
Yeah, well, yeah, radiation exposure is
stay there any period of time.
Yeah, is a serious concern for deep for long space flights. So to some extent, you're a little bit protected when you're in the space station because you're low orbit, and so you're still within the magnetic field of the Earth, and that helps to a large extent. Actually, the Chandra satellite, I didn't even mention, it goes 1/3 of the way to the moon, so we actually get above the protection of
the magnetosphere, understand, it's not uniform. So satellites going along, there's certain places across South America where it's not as protected.
Yeah, there's this thing called the South Atlantic anomaly that is an area of high particle background, and it varies with solar cycle. So there's actually one satellite that ran. Well, we're usually above that, so we're kind of out already in the radiation, so that's a big part of it. However, some of the low Earth satellites are affected by it. There was the satellite that ran for 15 years called the Rossi X-ray Timing Explorer that has made a very good 15-year map of the size and location of the South Atlantic anomaly by the fact that every time it passed through the South Atlantic anomaly, the satellite would become radioactive for 25 minutes. And by mapping that out, that was part, you just wouldn't take data as you pass through the South Atlantic anomaly, and you'd have on flow detectors.
Switches, you know, every 1,000 years or whatever.
Yeah.
If that switch happened, would that interfere with all the satellites and so forth?
It would alter the way you ran them a little bit. So yeah, so for some satellites, it's more an issue than others. I said there are some satellites that have made a very nice map of the South Atlantic anomaly based upon the measurements of the background particles and radiation that come. So all these are part of the engineering concerns. One of the things that we did not realize with the Chandra satellite early days was that not only are the mirrors very good at focusing X-rays, they're very good at focusing low energy protons. And so as it went through the radiation belt of the Earth, it would focus low energy protons onto the detectors. And that was not good for the detectors. So there was this little scary bit for a few weeks where the detectors were degrading. And then people were just like, what's happening? Until they realized that it's the low energy protons. So what we do now is that as we about to go into the radiation belts, you move the detectors out of the focal plane and you put the gratings in to act as a bit more of a filter, and that protects them every time you go through the radiation.
Can you say this talk will be a St. Louis Astronomical Society?
Pardon?
Can you say this talk will be St. Louis
This talk will be recorded, and it has been recorded, and we'll go. We can do that sometime, yeah.
we got McKen.
I tell you, these physics
I do have-
talks are great. I
You're
love
the best
them,
together.
but I love these
But,
talks. I love to learn something.
Hunter Orr's friend called me. He's gonna go on last night on.
Oh, yeah, that was, I do have I have a card in my office.
Thank you very much.
I'm going to walk your office.
Yeah, well, I'm going to end the online now. Thank you for coming, and we'll see you next time.